that it consists, if you have like n classes, there should be like n directories with the corresponding images of that class in that corresponding folder. Okay, so it has already figured out that it has like 2 classes. Note, I haven't said here like how many classes it is. It consists of like, it automatically checks like how many folders are present in your main folder or the spate images or whatever you have. Out of that, 80% it has selected for like training, so that is like almost like 18,728, and the remaining 4,682 are kept as like validation. If you want to know further details of this function, you can just look into this link, which gives you all the details. So let's go into visualizing the data. First of all, once we have the data set, you would like to like visualize and see like if it has like taken correctly or not. So there we are actually going to just use simple like a matplotlib pyplot. Here, like we are using the training data set. Okay, and for 9 images, I'm just showing you like 3 images, but if we are taking from range of 0 to 9, we will be just outputting like what are the images and the corresponding label, showing you like what is the class that they have given. So you can see here that once we run it, then it has taken like dogs as the class 1 and the cat as the class 0. Okay, so this is the entire part of how you do the dataset downloading and preparation. Then comes to the data pre-processing. So if you remember in yesterday's one, I said that if you want to create like more data sets, more training examples from the same data set, then you perform data augmentation. How you perform data augmentation? Something like flipping images randomly, or if you want to just do rotation, or if you want to maybe cropping. Those are the different ways that you can actually do augmentation. So how you do that in Keras, you have this function of this in layers experimental pre-processing. So all this comes under pre-processing. In pre-processing, you have different ways to do this augmentation. Ones that is being used here is the random flip in the horizontal direction. Note, will not do the vertical because it doesn't make sense to flip it like vertically. Okay, it doesn't correspond to a real image. And also there's something like random rotation. If you want to do random cropping also, that is also present as like a different function. So you can look into the details in the pre-processing. What are the different types of pre-processing in the augmentation that you can do? So now we have only just mentioned that what are the different ways that we will be doing augmentation. We haven't right now applied on the data set. Okay, so how we apply? So first thing is we want to just look into if we apply how it will look. Okay, so this is again like we are again visualizing the plotting. So this augmented images, the data augmentation of images shows it actually does the augmentation. As of now, we have created the function of what are the different types of augmentation that you will be doing. So here this data augmentation actually does the augmentation, and we are doing again, let's say for 9 samples that we want to create right from the same image. Okay, so we take one image and we do like 9 types of augmentation that we want to do, let's say. So you can see right now, like this image and this image are like flipped. Okay, these 2 images are like flipped, and this is something like a random rotation that you have done. Okay, so with all this, now you have, although it was the same image, but with this random cropping and rotation and everything, the your model will right now have like a obviously more extended data set, and each of these to the model are different from each other. And actually in the real world also, they can come out in all these different ways that you are clicking the picture. So it takes into account these types of variations also, because no one has said that you need to click a picture right in this way, that okay, so the dog will look right in this direction. It can be just in the opposite also, or it can be just a little bit rotated or cropped. So it handles both the way of overfitting and also creating your data set in a way that it will be like more real world. So now once we have this entire pre-processing done, so we want to like build your model. So to build the model, now we are actually first of all doing this augmentation. So once we have produced this entire function, we have wrote this function. At this point of time, we are actually doing the data augmentation on this inputs. Okay, and then at this point of time, we are doing the rescaling. So there are like these cases of how you can do the rescaling. Usually like in images, you want to do at least like one type of rescaling, which is something like dividing by the standard deviation. Okay, you can also do some sort of rescaling of like from 0 to 1. Although if you're working on images, it's not too much required, because the image pixels already comes in the form of like 0 to 255. Okay, but if you had some other type of ways uh, or other types of data sets, then you would also like to do the rescaling of just something like from normal deviation, normal distribution, you want to go to a standard normal distribution of x minus mu by sigma. Okay, so you can subtract your mean. If you want, you can also divide by standard deviation, and you can also rescale it to 0 to 1. Okay, to rescale it to 0 to 1, it's basically now dividing by 255, because that's a max that you have. But there are different other pre-processing that you can do. So if you just look into again at pre-processing, you will be able to see like what are the different types of pre-processing that people usually do, that is present in Keras. And people usually do most commonly like two types at least uh, of this pre-processing of x minus mu by sigma, which is like dividing by the standard deviation and subtracting the mean. Okay. Now when we have here, it comes to the, we are making the model, it comes to how, what will be the number of layers and what will be the different layers that we'll be adding. First of all, the most important part is adding the convolution layer. Okay, that is done by, in this layers you have like different types of layers that you can add. First is the con 2D. So 32 is actually the 32 filter size of 32 number of filters that you will be using. Filter size is like 3 cross 3, strides of 2. Padding, there are like two different ways. If you are doing valid, if you are just putting in valid here, which means that no padding will be done. If you are just adding padding equal to same, what it will do is it will keep the shape same. So in my first lecture, I actually told you about like what is like padding and how people do padding and what is the necessary conditions of why we need to do padding. Okay, so this is the thing of how to do this con 2D. Okay, and then comes the other layers that you need to add. There is a different other technique which I haven't went through in the previous lectures, in the previous videos, but you can look into something like batch normalization, which really helps to initialize and make your model to train and converge much better. So how to do that is basically, if you want to do batch normalization, which is like actually advised to do in all the cases, then you just add this again, this function. So you can think of, you don't need most of the times to know to write your entire function on your own. You can just call that function and that is enough. Okay, and then comes activation layer, and here you are mentioning like what is the activation function that you'll be using. So we are using here relu or rectified linear unit activation function. Okay, if you want to run the details of what are the convolution layer and what are the different options that are, or arguments that are present in convolution, you can again go to this link. Similarly, there are also links of this batch normalization activation. In activation, you will find all the link details of what are the different types of activation function that it allows. Okay, so this is like one convolution layer. So similarly, you have another convolution layer, and you can go with like similarly the pooling layers and everything. Okay, now I'm just going a little bit forward and then saying that, okay, so this actually like global average pooling 2D is actually just an alternative how to flatten the data. So once you have this entire volume, you flatten it to a complete vector. That's what you do that here using just like a average pooling 2D. Okay, so we are mentioning like what will be the final activation layer, what will be like we will be using as activation function. So the number of classes is 2. Actually, then you use a sigmoid function, where the softmax function is actually just an implementation when you have more than like binary classification, you go with like multi-class classification. So therefore, we are just putting an option of like whenever you have like only 2 classes, then go with a sigmoid. Otherwise, go with like softmax. Okay, and the units that you use is basically just the number of classes that you have. Okay, so here comes then of finally this dense layer, which is a fully connected layer, and before that you are just also adding a layer of dropout. So everything here basically comes in form of, you have the basic thing of layers, and the layers you have all the different types of layers that are present, something like max pooling or convolution or dense layer. You just add those layers accordingly. Okay, so now you have the final model that you make. Okay, So if you see here, this image size plus 1, which is like if you had this 180, 180, it's basically 180, 180. This plus tree consists of the 3 channels. And the number of classes that you have, since it was a binary class, so the number of classes that you have is like 2. So you need to just produce one probability of, let's say, if it is a dog, because dog was given as a class 1. So if you have just that one probability, obviously 1 minus that probability is basically the probability of it's a cat. Okay. So now you can just do this plot model, which will show you that entire of the architecture what you have built, and then you can like cross check if the architecture that you have built is the thing that you have thought of also like applying. Okay. Now coming to the training of the model. So in training, you, as I said, that you also do all this save epoch. So we are going with like 50 epochs, and we are saying that every, like, let's say like 5 epochs or whatever it is, it will be like just a parameter that will specify at every like 5 epochs we will just save our entire model weights. Okay, and we'll create a checkpoint so that even if your system is crashing for whatever purpose, you can right away start from the last save epoch. Okay, similar to like what you do when you are just saving your any files intermittently. So it's automatically saving your file intermittently whenever, and creating a checkpoint whenever you go into, let's say, like 1 epoch, 2 epoch, or let's say like 5 epoch, 10 epochs. Then finally it comes to compiling, and here you need to give, like, there are like different types of optimizers that people usually use. uh, like the most popular that people use is something like Adam. There are like other types of optimizers like RMS prop that you can use, but however, like Adam is the one which like people usually go with. I'm not going into details of what does Adam optimizer do, but just to let you know that there are different types of optimizers uh, to handle these optimization problems. Okay, to for better convergence, these are all catered towards to get like ultimately better convergence. So Adam plus I've just produced like, okay, like it consists of actually like 2 hyperparameters also here, beta 1 and beta 2. The default one is taken as 0.9 and 0.999, and you can go with just this default parameters if you don't want to change these hyperparameters, but all these are hyperparameters actually. Okay, the learning rate is the most important hyperparameter that will control like whether you are converging or not. Okay, because let's say like you have something like your function something like this. If you have like a too large epoch training learning rate, then your model can oscillate actually a lot. Okay, whereas if you have like a small epoch, then it will like gradually go to the optimum point. Okay, whereas if you have like very small learning rate, then your learning will be like very slow. So therefore it is like a very most important hyperparameter is actually the learning rate. Okay, so you, if you are seeing that your models are not converging, or if it's a diverging, then you can change your hyperparameter accordingly. Then coming to the loss that you'll be using, since you are doing this classification, usually you go with the cross entropy loss. There are 2 types of loss that you can use. They are basically simple and related, but whenever you're doing the binary classification, then you go with the binary cross entropy, and whenever you're doing this multi-class classification, you go with the categorical cross entropy. Okay, and this is only for classification, so therefore these are the probabilistic losses. When you are doing something like prediction, there you need like regression losses, something like mean square error or some, or like mean absolute error. Okay, but whenever you're doing this classification, either if you have like 2 classes, go with like binary, or otherwise go with the categorical if you have like a multi-class classification. Then coming to the metrics, like what is a metric that the model will use to calculate your training accuracy and your validation, how well the model is performing. Here people also go with usually this accuracy. You can have many other type of like metrics that if you want, um, these are different metrics that are available, but I would say like if you are just going simple, then go with the accuracy. Okay, so then it comes to finally fitting the model. So after all these things that we have like specified, so you will fitting the model using the, so you are using the train data set, validation data set, and specifying the number of epochs is 50, and the callbacks is basically like it will save at like how many epochs. Okay, So then your model will, like with this model under dot fit, it will basically fit your model, and this entire process of training will start. Okay, it depends on like how much large scale is the data. When you have that, then you go with finally, if you want to just infer your model, then you just run the model, run on a random image that if you want. So let's say on a random image, any random image, you want to infer like what is the probability that is showing that it is a dog or a cat. So first you just convert into a, in using this image to array, you convert this image into the keras format. Okay, and then this model dot predict is the main function that you use to predict. So the model already has all the weights, and then this image array is the image that you have loaded. Then you predict the class. So it consists of the predictions. So the prediction 0 is basically the prediction that if it's like a cat or a dog. Okay, so since it was a cat, so you can see that right now after like training, it will show like it's 84% probability that it's a cat, and it's a 15% probability that it's a dog. So therefore it has made the correct decision that if it's a cat. Usually you can go with, like let's say like whenever the probability is 0.5, you give the class, you give the assignment to that class. Okay, so if it is 0.5, more than 0.5% probability saying that it's a cat, then you go with a cat. Otherwise you go with a dog. Okay. So this gives you from the very basic of how to do like an image classification from scratch. Okay, now coming to a little bit different example, but it's almost also the similar, where you're also using the keras. So the first part is like initially same. Here, like in fact, there are many other data sets that are already available in keras. One of the very popular data set actually called a CFAR10 dataset, which consists of 10 classes, total of like 60,000 images. They are basically of the cats, dogs, aeroplanes, trains, or other of these classes. They are very small images, actually just 32 cross 32 cross 3. But all the initial models that people used to build were based on CFAR10 dataset. So that's why it's a very popular dataset. Okay. Here I'm, as you can see that right now I'm also normalizing the pixels value, dividing by 255, so that the pixel values right now varies from 0 to 1. It helps, or most of the times it helps you to have like a better training process. So now only little bit different that I'm showing here is to have like a much more just an intuitive way of how to do like adding the layers one after another. So you can see that I'm adding the conv2d, number of filters, then the filter size 3 cross 3, activation of ReLU, and then is the given input shape, which is a 32 cross 32 cross 3, which is the input shape of the CFAR10. Now we are doing this max pooling of 2 cross 2. Just I will change to a laser pointer, and then you are using again the conv, then again max pool, then again conv. Then we are doing the flattening, converting this entire volume to a vector, and then you are finally using the 2 fully connected layers. Last fully connected layers consist of 10 units because it has like 10 classes. So this is a much more easier way of how to just add layers like one after another. All these things you can actually get, these are taken from this code. It also comes with a Google Colab link also down here. Okay. Once you have the entire model built, you can do the model.summary, which gives you the entire summary. As you can see, this consists of the conv2d, then the pooling, then conv2d and pooling, and then flatten and 2 tens. Okay. Also, you can see that what are the different output shapes. It gives you like a real understanding of how is the architecture being built. Of, as you can see in the max pooling, I'm just doing like a dividing into like making it half of the size from, so from 30 cross 30, I'm going to 15 cross 15. And then in the conv size, I'm just reducing a size a little bit to 13 cross 13 again, and then I'm doing again a half, then again conv2d, and then finally flattening. And also, as I say, the number of parameters that your model need to learn, you can also just get right away from here. And you can see from here that the number of models that you have to learn increases like so much here right at this dense level. Okay, it had in the initial ones, it had just a small number of layers, but whenever like your size is like decreasing but your number of filters are increasing, then the number of weights that you need to learn increases a lot more. So that's why like you have like 18,000, then 37,000, but with the dense it goes to an immense more. And then the final dense is obviously just doing the final class probability. So this gives you entire thing of learning from scratch. Okay, if you want to build your model from scratch. But as I had also mentioned, that whenever you are going with building a model, then you don't go with learning everything from scratch. You usually go with something which is like transfer learning. So how we can do transfer learning? So let's look into. So here, this is actually the data set that you are using. Again, the scat process dogs. And I said, like, you can use here, like you can already specify in this way of this. This is a different way of directly in TensorFlow. And you can see here that the split we have also mentioned, you can mention this way of the training is from 0 to 40%. And then the validation will be from 40 to 50%, and the test will be from 50 to 60%. Okay, since we are going with the transfer learning, that's why we didn't went with this entire data set, but rather we wanted to work on a smaller data set and still see that it is working or not. Okay, so total images that it had was 25,000 here. Out of that, we have chosen like training as like 9,300, validation as 2,300, and then test sample size 2,300. So we haven't used the remaining 40% of the data to make the data set smaller, but still see like if it works using the transfer learning. So now you basically, as I said, like in transfer learning, you start your model from a base model. Okay. So in this case, you can just use any model that you want. Here they were using this exception model, which is another type of like model that came out after all this. This is a similar type of like say like AlexNet or like VGGNet. So it's a similar other one is like exception. Okay. The weights are basically the weights that was trained on ImageNet. I'm giving the input shape as 150 cross 150 cross 3. Include underscore top equal false. What it means is the last final layer, output layer that was usually present. I'm just removing it because the last layer actually consists of the final classification layers of giving the final probabilities, which you do not need because the ImageNet classification is like 1,000 classes, whereas like your classification will be a different number of classes that you want to predict. Let's say here just the cats and dogs. And now I'm freezing the model. So base underscore model equal training equal false. Where I froze the model, I've said that no, you will not be training the entire model. And then this again thing of applying the data augmentation and first of all, just inputting, just taking the input. Okay. So here, like as I said, like the two different other normal ways of how people also do like normalization is x minus mu by sigma of doing the standardization. So here I'm first calculating the mean and then the variance. Okay. And I'm using the normalization of just converting it into like set weights of mean and variance. Okay. So this is the way of how to do like normalization between like, so here they were actually doing the normalization from -1 to +1 and then also from x minus mu by sigma. Okay. So there are like two different ways that you can do the transfer learning. First is a fixed feature extractor. So you just remove the last layer and you take the features from there. Okay. So this is how you basically do that. So you have the model training equals false. Okay. So I have already said that we will not do the base model training. So we are taking out the final model. Okay. From this average 2D, and then we are applying a little bit of dropout. The final dense is basically just adding a dense layer of the classification that you want to do. Okay. So if I do this model summary, so you can see that this was the entire model that was there. So out of that, I took here, so it was the exception model. I converted that into like global average pooling, converted it to a 2048 dimensions, just using a dropout to handle overfitting. Then the final dense layer showing like just converted into like a one class probability of if it's a cat or a dog. So number of parameters that were there were, as you can see, there were a lot more parameters of something like 20, 100,000. Out of that, the trainable parameters that you have is only for the last layer, where you have this 2048 as a final layer. Okay. All the other weights are kept as like fixed. Okay. So the trainable parameters are only this 2049. All the other parameters you will not be training. So that's what is a fixed feature extractor doing. Okay. Then you do this exact simple thing what you had done before. Also, you specify the optimizer, you specify binary cross entropy, and then what is the loss function that you'll be using, and then the accuracy metric that you'll be using. Okay. So this entire thing remains same. what we had also seen in this classification from scratch. So now let's look into the transfer learning by fine tuning, where like instead of just changing the last layer, we will be fine tuning our entire model. So in this case, the change that you do is like base model dot trainable equal true. So we see that the ultimately we will also train the base model. All the others remain exactly same. So here now, if you do the model summary, you will see that only thing that it doesn't train is actually something is a batch normalization weights, because it becomes very difficult when you're doing the transfer learning to also take care of the batch normalization weights. So this thing is automatically handled by the keras. But the change that you are seeing here is except the other than this 2049, it has all the training that it needs to be done on this uh, weights that are present also on this base model. So this is the difference between fine tuning and fixed feature extractor. And it handles automatically just by changing this base model trainable equal true or false. Okay. If you're interested, you can actually go into this link, and then it has all the details and the final code that works. I've just shown you the most important snippets here. So now I'll go a little bit into like object detection and show you the code of how to write like object detection codes. Okay. So in object detection, I will go a little bit faster here because this lecture is actually about rather than the coding. So, but since I have not covered object detection, so I'll just cover a little bit in object detection before going into the code. Okay. So usually if you want to just do a classification, you have just the image, and if you want to say if it's a car or not. A more extended task is instead of just doing the classification, we also localize. We'll say that where that car is located. So these are all when you are doing the single object. There's only one object in this class which we are interested in. But if you have like multiple objects, it's something like object detection, where you want to say that, okay, so there are cars present, but there are multiple cars present. These are the locations where it's present. Also, there are some birds or duck which is like present. Even more extended part is actually something like segmentation. I had talked a little bit of that in yesterday's lecture when we say that in pavement cracks, how we want to like detect. But this is something like in a pixel level, rather than just drawing bounding box, we are doing the pixel level that this is where the car is, this is where the bird is present. And if we require, we can also say that this is where the road is present, something like that. So this is something like segmentation where you're doing a pixel-wise classification, let's say. So localization, you can do in like different ways that you can localize. Always you need 4 coordinates. So 4 coordinates you can give in just in the 2 of the opposite coordinates of the x1, y1 and x2, y2. You can also give like just to the x1, y1 and then the width and the height. Other way that people also do this bounding box coordinates, if you give the center and if you give the height of the width. Note any of these informations that you have. So let's say from this information, you can easily get this information. And similarly, from this information, you can also get the third information of where is the center. Okay. So these are different ways that actually people use to localize the object. So when you're doing this localization, there's like 2 different subheads that people use. Okay. First is now you have to do first the classification of like where the what is that object which is like present, which is something exactly like classification. And on the other hand, if you want to find out the coordinates, it's actually, you can see that it's a continuous output. So it's exactly similar to like regression of saying like this is the point of the coordinate of this box and this is the other coordinate. Okay, so it's something like a 4-dimensional vector that you want. Okay, so that's why like people say that whenever doing localization, it can be divided into 2 parts of class. Excuse me. Because there are 2 parts of the classification and regression. So this came out from this paper of the overfit, which was one of the first papers that came out after this AlexNet showing like deep learning models for localization task. So then you do some sort of sliding window saying that, okay, so in previous location, this was a probability that here is a car present. In this location, here is a probability that car is present. Similarly, for all the 4 different locations that if you want. And then at each point, you just do, for each window, you find out the coordinates of the bounding box, and then you merge those coordinates critically to find out the final output box. Okay, that's how like in overfit like people did. And I'm not going obviously to the too much details, but what you can see is the localization error. So first in AlexNet, it went into the 34, and then gradually, just with higher layers or deeper layers, just the error decreased a lot. And then as with like ResNet, it came out with a so much deep layer with a little bit modifications also. And then the localization just error rate dropped a lot. But however, when you're doing this regression, then it becomes like difficult if you are doing this detection as a regression, because then since you have like multiple objects, so that now output size will be like different. So in this case, you have like 5 objects. So your output size will be like 4 into 5, because for each box you have like 4 coordinates. But if you have like 2 objects, the regression output will be just 4 into 2. Therefore, it becomes very difficult when you don't have a fixed output size to do as a regression. And if you are doing the classification and sliding window, it becomes like very slow, okay, because you have to do consider of too many aspect ratios, too many sizes of the sliding windows. So what you do is something like a selective search. In selective search, what we do is we first try to find out the region proposals or proposals of where objects might be present. So we just go with little bit of segmentation of finding out some of the edge cases, as you can see, and then we do our object detection using like sliding window or whatever approaches just in those regions, because we have first selected doing the selective search where are the objects might be like present. So something like, let's say you have like a table, it's obviously also hierarchical grouping that we know. For in a table, on the top of table there are like bowl and a glass. On the top of the bowls there can be like spoons which are like present. So similarly on the background, you can have like the ground, and then on the top of that you can have like ships or persons or maybe like mountains on the background. Okay. So there are different types of object detection modules that are like present. The very first that came out was something of this RCNN, where they actually did a selective search and then they put a convnet on the top of that to, and then with the convnet they use this two classification, first with the regression to find out the bounding box positions, and then this SVM was just doing a classification of what is the class that is like present. Okay. So this just shows a little bit details of, as I said, like binary SVM that they were using of whether it's a cat or no cat, if it's a dog or no dog, something like that. And for finding out this bounding box, they were doing this bounding box regression. So if you're looking into the RCNN results, so this is the mean average precision. So the higher it is, the better it is. So previously the accuracy that they used to get, or the precision that they used to get, was something like just saying 30%. With RCNN, it jumped a lot, because this was the first and they actually showed with deep neural networks how much advantage that it can go. And then in later years, even just with the same architect, same type of region proposal, but just with the deeper layers of VGG instead of AlexNet, they achieved a higher accuracy. So this show that if you just have like higher layers, then the accuracy can also improve. But however, one of the main disadvantages of RCNN was it was like very slow. So let's say like with each image, it used to take something like 47 seconds just to run the object detection on just on one image. Okay. So therefore, like what it did, they came out with a more advanced versions of something called like fast RCNN. In faster RCNN, they did only like one coordinate rather than multiple coordinates that you can see if you're showing here. They were like multiple coordinates. So here I'm just going with like one coordinate that reduced in, and then also they had like a end-to-end trainable model rather than having like a regression model and then an SVM model, and then things are not talking to each other. The training is not going in simultaneously. Okay. So it was like a little bit faster compared to like 50 seconds. It went into like 2 seconds, but still, actually, it was still too much. Like if you consider like just like 2 seconds just to run on one image, and if you were to run on videos, it was still very slow. Okay. But out of that, another important part was if you're just doing this running other than this region proposal or the selected search, it was a 0.32 second. So a majority of the time was actually find out this region proposals using selective search. So in the faster RCNN which came out, they took away this region proposal. They put a CNN for doing this selective search of region proposal, and then the amount of improvements that you got, although the accuracy didn't improve like too much, but it became like much more faster, and that was like required if you want to do like object detection on, let's say, videos. So this was just a very quick background of the different object detection. There are many other object detection models that are like available, but the first ones that came out was actually this RCNN family. So if I want to go into the codes, here also like TensorFlow actually gives you a very efficient way of how to do like different types of object detection modules that are like present. So you can go into this link to get all these object detection modules. So in this link, you will already also see like running like Google Colab, where you can just click to run your model in Colab if you want. Okay. So all this object detection hub that is present, it consists of all the different models trained on a dataset called COCO 2017 dataset, which is a very popular dataset that people use. So here you can see all the different models that are present. You can see somewhere here this faster RCNN, then there's something called mask RCNN for the segmentation task. Other of the very popular and useful are something like the single shot detector SSD, which is little bit equivalent to YOLO in the case that it is like much more faster compared to the other this faster RCNN cases. So if you want, you can just go with SSD also. Okay, it gives you all the accuracies and along like what is the speed of like what does how many milliseconds it take to train test on each image. Okay, and this RetinaNet and all those are the base models that they have used to train the model. Okay, so all this you can just use any one of that based on how much speed you want and how much accuracy you want. Okay, going into the code, the initial first part is just to do the some of this import of what are the things that are required. The next part here, you actually do some sort of like finding out all the utilities that are required of it. Just remains same whenever you're doing any type of this object detection. These are the important where you actually say what are the different models that are here. And if you go into the link, it will give you all the different models. You can just select a few models if you want out of the all different models that are present. Then these are actually some of the parts of just doing like a visualization tools that you will use to see like how the objects that detection has performed. The main part comes in here when you're doing this detection model and loading the pre-trained weights. So in this link, they were actually using just this model. Instead of this, you can choose any other model from the list that is present here. Okay. So I'm specifying the model name, and then with the all models that is like present here, it will take the weights accordingly for the given model display name that you have chosen, and then it will, I'm just printing the model name here. Okay, then I'm loading the model. So this is like this portion takes the loading the model, and then I'm also loading the image on whichever image you want to do this object detection. You are just loading the image here. Okay, then this one is actually doing the final visual inference and the visualization, where like if you see like this one of image.copy, after that you are this doing of this results, it will just show you the results of, at this point you have created the results for that image, and once you have the image, then you just do the visualization. Okay, there's some sort of visualization they also do for the human pose key points, which is not too much important, but if you look into here, you will see like if you just run this entire thing, you will see something like this on a given image. It had like COCO concept of 80 classes. Majority of the classes that you see, you can just do here. Okay, so it consists of this image bounding box pretty well, corresponding with also with the probability of what is the probability of person. And these are something like these key points of like what is the human pose. Okay. So if you are looked into my previous yesterday's lecture, there was also of this YOLO. YOLO, it is actually built on another platform called Darknet. Therefore, it's originally available not directly in like TensorFlow, although people have done written their own codes where you can also do in like TensorFlow. Okay, but if you want to just run your YOLO detection model, then I will say like rather go with like this link, because this is like gives you a complete update of all the updates that has happened. As I said, like YOLO came out, then V2, then V3, and then very recently V4. So all the updates with a lot of recent improvements that have come out, this comes out in this link. and it's like, and it works both in like Windows and Linux. Even if you don't have GPU, still you can run. It gives you off, like if you don't have GPU, you basically compile your darknet using this GPU equal to 0. And this darknet is actually the platform that is being used for YOLO. So that's a little bit different platform compared to like Keras or TensorFlow or PyTorch. Okay. So you can run on any video that if you want. Okay, let's say like if you just want to run on a video, you just give this command and then it just runs directly on the video. Okay. And this also shows you if you want to just run on any image, you can just run, you can output the coordinates, you can run on a video and everything. Okay. So if you're just wanting to do just a very simple test on an image without training your model, you can just directly do that either in like Windows or darknet, Windows or Linux platform. Also, like this, if you go into this link, it will give you all the details of how to train your model if you want. The only thing that is present is like you have to first of all prepare your data set in the format that's required for this YOLO to take. Okay. Along with that, there is like also YOLO is present in like TensorFlow, but this comes out from individual people rather than coming directly from, like, let's say the previous ones that I had like said in object detection TensorFlow, that coming directly from TensorFlow. So they are like much more reliable. But these are coming from individual people who have like created their own models and have their made their codes open source. So you can look into this TensorFlow YOLO v4 TF Lite, which gives you like how to run YOLO on TensorFlow. Okay. But if you want to just run on any image and you don't have a constraint of you are wanting to use TensorFlow, then I would say like rather go with the previous one because that's much more updated and it should be much more faster. Okay. So that's all. One thing that I would like to say is like all the codes, most of the codes are available in online. One good thing of this entire computer vision community is whatever they come out with, if it is like really useful, they make their codes open source. So you can directly take their code, play around with it, and then see like how it's performing. So now I will be open to any questions.
Thank you, sir. The session was really helpful. All the participants will surely benefit from the lecture. We'll take the questions now. I request the participants to write their questions in the chat section. Uh, so there are no questions as of now in the chat section. So I had to ask you a question. Can I ask?
Yeah, sure.
Yes, sir. So can we develop the CNN model using graphical user interface of any software? Is it necessary to go for programming?
It is usually, I am not aware of anything, something like just like a GUI based where you
Yes.
can just run your model. Might be like later in later years, they might be just coming off like Java
Okay.
had their own machine learning, like you can just do on, I forgot like what's the machine learning tool that they had.
Yes.
But I would say like if you go with like MATLAB, they had like a lot more resources that you can use where it becomes much more like a user interface friendly.
Yes. So
Okay.
can the CNN be developed in MATLAB?
So I have not too much worked on MATLAB, but as far as I'm aware of, it is like already CNN is present in like MATLAB with many of these resources. Okay.
Okay, sir.
So you can try to use MATLAB where like different of these models are like present, and it
Okay.
should be like a little bit more easier. Only thing is like most of the times the updates that come out are
Yes.
usually uh, not available right away in like MATLAB because people might be just writing their code. So Python is since the open source, so that's why
Yes.
like people usually go with maybe like Python, and that's the most preferred platform that I would say when people are right now doing all this in computer vision community.
Yes, sir. Thank you, sir. So there's a question from Shobna Purushothaman. Uh, she's asking, sir, if we are using online codes, means no need to assign any weights as discussed in previous sessions.
Yeah, so like usually how it goes is like if you are just wanting to do something like a basic classification, let's say where the car is present, if a car is present or not, if where the person is present, then in those cases these are like so popular classes that you can right away use the Coco dataset, okay, because it already had the classes. But if you're going with something of let's say finding out cracks, pavement cracks or something like that, In that case, you have to train your model. You can definitely use like transfer learning to train your own model, but then you get all the weights uh, which you will use for your own model, because these type of cracks or no cracks will not come in the COCO dataset. But the simple things of detecting cars or detecting like pavement location, or maybe like persons, that you can directly do with the COCO dataset.
Okay, sir. So there's another question from Udyan Shrivastava. He's asking how well does the algorithm stand under detecting similar yet different objects?
So like it depends on like how much similar and different that you are wanting. So let's say like I want to find out like if it's a car or a bus, which are actually all the different same, they are all vehicles, but they are different vehicles. In that case, the COCO data sets are should be working like quite decent enough. But if you consider of let's say like a car, I want to find out if it's a maybe a sedan or a SUV. In that case, might be that you have to make your own model train using like transfer learning to make it like work. Okay, but it depends on how much data set that you had, and also how much similar but yet different objects that you are looking into. If you have a large scale data set, then the model will still do a quite a decent job, I think.
Thank you, sir. So there's another question from Virender Singh. He's asking, is there any thumb rule for deciding on weights?
So weights are actually learned from training. Okay, so you do this entire training and then you learn the best weights. Okay, one important thing that you have to look for is like how you're initializing the weights. So therefore there is different techniques that people use to have a better initialization of the weights. So like this batch normalization takes care of that, so it doesn't matter too much of how you have initialized the weights. People usually go with like random weights, and since they go with random weights, therefore it becomes like very critical of like what is the weight that they have started on with just using like randomly. But using like batch norm, it doesn't matter also like how much of random initialization that you have used on the weights initialization. But once the weight initialization has been done, then you do this entire training to come up with the best weights. Also, like if you go with like COCO dataset and all those, there you already have the weights. One thing that I'm not sure if you are asking of like which model to use, if that's the question that if you are asking, then it depends also on what is the accuracy. Each of this also comes with like what is the accuracy on the COCO dataset. So if you want a higher accuracy or if you want to like higher speed, you can choose your model accordingly. Okay, because each of these models has a different weights and therefore it will perform differently. That's where the accuracy is actually different. You were muted right now.
Ah,
Sorry, sir. Thank you, sir. Thank you for being part of the short-term course. We are highly obliged. Thanks a lot. This was
Yeah,
really a very fruitful session. I'm sure all the participants will agree with it. We have really got very good feedbacks for your sessions. We thank you for being part of it.
yeah. Thank you everyone for actually inviting,
thank
and thank
you.
you all the participants for participating in this course and also to my presentations.
Thank you, Professor Pranamesh Chakrabarti, for giving maximum lectures in the course. We
Yeah,
had
thank
three lectures. I have a special thanks for you because you have accepted my invitation for maximum number of lectures. Thank you very much,
yeah.
sir. See you soon.
Thank you everyone.
Okay, thank you.
Yeah,
Thank
thank
you,
you.
sir.
Thank you.
Okay, so the next session will begin at 11:30 a.m. Please join 5 minutes before the start of the session. Thank you all for being part of this.